This week's lecture is going to deal with high pressure processing or high hypobaric pressure processing. And as we begin to look at this, I think one of the things to note is that actually this technology may not be quite as new as perhaps many of you may have thought. High hypobaric pressure processing or Pascalization actually dates back to 1884, and one of the first individuals to actually do any research looking at hypobaric pressure processing was Height. And back in 1899, actually, he used this technology to improve the keeping quality of milk. And he followed that up with some research in 1914, where he actually demonstrated the susceptibility of fruit-borne organisms to hydrostatic pressures. Current interest in high hyperbaric pressure processing is based on two major points. One being the consumer's demand for minimally processed foods. I think if you are a consumer and you are purchasing food, people are looking for food products that are more like fresh. And to be able to do this, the technology that's actually required is some that actually requires minimal processing. And in many instances, this minimal processing is a result of using some of the newer non-thermal processing technologies. And then also the fact that there's been a reduction in the cost and the greater availability of the actual processing equipment to carry out high hyperbaric pressure processing. Some advantages of it are certainly that it can be applied at room temperature. And with the exception of some vegetables, the shape, color, and nutrients of most food are unaffected. And I have some more to say about this and provide you with some examples of this later on in the lecture. Products have been commercially available in Japan actually since the early 1990s. The types of products that we see in the marketplace over there as a result of high hyperbaric pressure processing included fruit purees, jams, fruit juices, and rich cakes. And if you look at this, in most instances we're looking at acidic products, and in some instances we've also looked at using this technology for acidified food products. There is no shear force created when we carry out high hyperbaric pressure processing. Thus, any moist food can be processed without it being actually crushed. An example would be that one could actually process grapes using a hyperbaric pressure, and the grapes are not going to be crushed. They're actually going to maintain their shape through the process. Some approvals for high hyperbaric pressure include lobster, and my question to you, what might be the application of high hyperbaric pressure for processing of lobsters, although I don't know as anybody's actually using this technology. Provided this picture of the lobsters because it does show you lobsters of different colors, so some of the unique color pigments that we might find in lobsters. Oysters, certainly there's an application for approval with oysters, and this application has actually been used commercially. It's been approved for fruits in the United States, both acid foods as well as fruits, and then also acidified foods. If one looks at some pictures of oysters that have been processed by high hyperbaric pressure, you can see on the left-hand side, you can see the actual oysters are band, have a band around them before they're actually processed using high hyperbaric pressure, and this is to prevent the shell from opening. And on the right-hand side of the slide, you can actually see an oyster that has been processed by high hyperbaric pressure, and it maintains its quality in terms of being a product that one could actually consume as a fresh oyster that has not been cooked in any manner. So if you like oysters on the half shell, this is one way that one can ensure food safety of these particular oysters. And to answer the question that I posed on the previous slide, this technology is used in oysters to ensure that any potential Vibrio foodborne pathogens that might be present in the oysters would be destroyed. If one looks at the types of pressure we're talking about and providing high hyperbaric pressure, if one was to think of 3 Indian elephants, which weigh approximately 5 tons each, and these 3 elephants were standing on an 18-millimeter diameter disc that we can see down there in the green, and the amount of pressure that would be exerted on that disc would be about 600 megapascals, or about 87,000 pounds per square inch. And this is around the range that or even slightly higher than the range that is used for some of the food processing applications that we have currently in the market. The equipment required for high hyperbaric pressure processing includes a metal chamber. Most often it's going to be a steel cylinder. You need pressure pumps that are used to generate pressures of several hundred megapascals, and that's what the MPa stands for. 1 megapascal is equal to equal to 10 atmospheres, and 100 megapascals is equal to 1 kilobar. Come up and come down times for pressure are very important, and the come up and come down times typically are going to be 2 to 3 megapascals per second. You need the presence of typically a low compressible liquid, and most often that liquid is going to be water. And the pressure may be applied by two mechanisms. It may be applied static, or it may be applied in an oscillatory manner. So it can be oscillate, pressure on, pressure off, pressure on, pressure off, or it may be continuous pressure, which is called static. In a batch processor, this is a small batch hyperbaric pressure processing piece of equipment that one might find perhaps in a pilot plant. Ohio State University does a lot of work with these types of technologies. And you can see you have a pressure chamber, which is going to be steel, and you can see the gentleman looking into it. The food happens to be, in this case, in a bag. And then it's sealed in that chamber. We would have water in that chamber. The pressure would be applied, and again, it could be applied statically, or it can be applied by oscillation. And then during that process, the product is actually processed using hyperbaric pressure. If we look at a potential commercial line, or a schematic diagram of a commercial line, this would be a case where we're using a single unit, which would be by batch, using it in batches. And one can see that on the left-hand side, the food containers containing the food that's going to be processed is put into trays, and those trays then can be stacked. And then that stack of food product can be lifted and put into the high hyperbaric pressure chamber. Once it has been processed, it can be removed from that high hyperbaric pressure chamber and then moved over on the line, the conveyor belt, and then be unloaded from the containers. So this would be a batch process. We could also have a continuous processor, and in a continuous processor, the food product is continuously coming in and being processed and then being removed from the hyperbaric chamber. And we can see an example on the right-hand side of 3 of these continuous high hyperbaric pressure chambers. We have a movable divider that's used to push the food in and out, and then we have pure water coming into this chamber to actually maintain and push the actual divider. So we're using UHP pure water, and that's going to make that divider go up and down as we push it in and push it out. And if we look at a flow diagram of a continuous process schematic from Flow International Corporation, incoming product on the left is held in a holding tank, and the blue is the line where the food product is actually going into the continuous high hyperbaric pressure chambers. The red is the product as it exits those chambers and then goes on to a surge tank where it's held, and then it would have to go into an aseptic processing unit to be actually packaged. So you have the product, packaged product coming out on the right-hand side. But you have a low pressure transfer pump which will push the product from the holding tank through the flow line into the continuous high hyperbaric pressure chambers, and below that you can see you have the high pressure pump that's going to actually be the source of the pressure that's going to be used to process that food product, and then it's going to be exiting and going further to be packaged. Types of processing: you can have in-container processing, where the product is actually in a container or bagged when it's being processed. The other would be bulk processing, where you have a product that's actually being processed as it flows through the individual chamber. And there are some advantages and disadvantages of both of these types of processing methods, and we'll talk about those in the next few slides. So in container processing, the advantage is it can be used for all liquids and solid foods. There's little risk of post-process contamination because the product is already in the container prior to the processing occurring. No major developments needed for high hyperbaric pressure processing with product in container, and certainly it's easier to clean the chamber using in-container processing because the food product actually never comes in contact with the inside of the chamber. The limitations of in-container processing include complex material handling, which would be very difficult to do in this. There's little flexibility in the container choice that one has, and there's greater dead time in the use of pressure vessel because you have to load it and unload it after each processing step. Bulk processing, there are some specific advantages. Simple materials handling. There's greater flexibility in container choice because the actual packaging of the product actually occurs following processing. Maximum efficiency in the use of the high hyperbaric pressure vessel volume, because there's minimal vessel dead time, no opening and closing of the vessel, faster loading and unloading using this technology. But there are as well some limitations of bulk processing using high hyperbaric pressure, and limitations include it can only be used for pumpable foods because you need to be able to pump that food through the chamber. It requires an aseptic filling of containers, so you have to have an aseptic packaging unit in addition to the actual high hyperbaric pressure processing equipment. This allows for the potential for post-processing contamination, and it must be designed so that you have clean in place, a CIP, and sterilizing in place of the actual equipment. The next 3 slides actually will take you, these are hyperlinked to videos that you can find on YouTube that actually show you some examples of high hyperbaric pressure processing. This first one actually shows you seafood that's processed using high hyperbaric pressure processing. Certainly I find the videos very useful in that they actually show you how that technology works. Which is sometimes, I think, more useful in actually talking about it using a series of slides. The next video, again, it's hyperlinked and will take you to a butterball facility in Canada where they use hyperbaric pressure processing. And these videos are 3 to 7 or 8 minutes, so they're very, very short. And finally, there's another example of a Japanese seafood processing with high hyperbaric pressure. Again, this one is in Japanese, but you can actually follow the process as the product goes through the process of being used in high hyperbaric pressure processing vessel. So as we look at studies that have been done looking at how high hyperbaric pressure processing works, as well as how effective it is on spoilage organisms, as well as potential foodborne pathogens. Certainly, there have been a number of studies that have compared static to oscillatory methods. One example of this would be using yeast, Saccharomyces ballii. It was in liquid medium, and also one using spores of Bacillus stereothermophilus, and 10 to the 6 spores per mil were destroyed after 6 5-minute cycles at a total time of 60 minutes at 600 megapascals. Oscillatory has been found to be more effective than using static processing methods. So bringing the pressure up, then releasing it, bringing it back up and releasing it through several cycles has been found to be much more effective than just maintaining that pressure over the whole given time of the process. High hyperbaric pressure processing is equally effective on both liquids and solid foods. For typical antimicrobial actions, pressures in the range of 200 to 1,000 megapascals are needed. In most instances, we probably need more than 200 for applications that have been looked at, and most of the applications probably using less than 1,000. The principles and effects of high hyperbaric pressure on foods and organisms, it's non-thermal, so covalent bonds are not broken in this type of processing. In general, flavor is unaffected. We'll talk a little bit about a slide later on in the presentation that will give an example where it could be. Hydrogen bonds appear to be strengthened, And between 400 and 600 megapascals, proteins tend to be denatured. And this would include certainly the proteins that are associated with any spoilage or potential foodborne pathogens that might be associated with that food or food product. Up to 450 megapascals will inactivate the vegetative cells, and certainly the order of decreasing in sensitivity. Eukaryotic cells are more affected than gram-negative bacteria, which are more affected at the same pressure than fungi, and fungi are more affected than gram-positive bacteria. And then finally, the least affected at a 450 megapascals would be bacterial endospores. So gram-negative bacteria are more easily destroyed using a high hypobaric pressure than our gram-positive bacteria. And then finally, bacterial endospores are the least affected. Cells in the stationary phase tend to be more resistant than those in the log phase, which probably compares favorably with other technologies, processing technology, preservation technologies that we've talked about. Cells certainly, as they're growing and dividing, tend to be more sensitive to food preservation technologies than they do when they're in the stationary or resting phase. Microorganisms in dehydrated foods are highly resistant to high hypobaric pressure, so they tend to be barrier resistant. Barrier resistance increases as the water activity is lowered. So in a food product where we have very, very low water activity and we would have potential spoilage of foodborne pathogens present, not going to be affected very greatly using this type of preservation technology. That's why we typically use it with foods that would have a fairly high water activity. Between 450 and 800 megapascals are needed to destroy spore formers under optimal conditions, and some of them may require greater than 1,000 megapascals. The cell morphology is altered using high hypobaric pressure, and ribosomes are destroyed. And my question to you is, if we destroy the ribosomes, what does this mean in terms of cell survival? Membrane liquid protein complexes are changed, and we have seen leakage of nucleic acids when we use 200 to 400 megapascals of pressure. Also, ATPase is inactivated, and what are the implications, again, to cell survival, potential pathogens, spoilage organisms as a result of loss of ATP activity. Oxidative enzymes of fruit, though, are barrier-resistant, and I'll give you an example of this when we talk about this later on in the presentation. High hypobaric pressure is generally ineffective against bacterial cell walls, but there is synergism certainly with other types of preservation methods that you will have talked about through the semester, with bacteriocins, nisin, as an example. With heat, low pH seems to be more effective, the presence of carbon dioxide, the presence of the enzyme lysozyme, and thus this technology could be used as part of a hurdle system that, again, you should have talked about during the semester. High hypobaric pressure can lead to those sublethal damage. And my question to you related to sublethal damage is, what are the implications in food products, particularly as it relates maybe less to food spoilage microorganisms, but to potential foodborne pathogens if we have them sublethally damaged? Endospores are highly resistant, but when destroyed, it appears to be the result from the actual germination of the spore and then the destruction of the vegetative cell that has been generated as that spore has germinated. The D megapascal values for high hypobaric pressure processing have been difficult to calculate, much more so than using thermal processing methods, because we get a tailing of survival curves as we look at particular, say, foodborne pathogens. Researchers have looked at Listeria monocytogenes and Salmonella serotypes, both in cultural media as well as in food systems, and looking at this tailing and looking at what the D values would be for megapascal treatment. Metric in his cohorts in 1989 were looking at the Salmonella serotype Typhimurium, and they were looking at megapascal levels of 340, and they were looked at both this particular Salmonella typhimurium in buffer and in chicken. And in these two instances, the time frame for destruction, DMPA, was 7.4 minutes in the buffer, and then when you get into chicken, which is a more complex, certainly food matrix, was slightly longer at 7.63 minutes. Salmonella stereotype Steffenberg values were 4.4 in the buffer, but when we put it in chicken, again with a more complex food matrix, it took 7.13 minutes. Another study in 1998 looked at, again, Salmonella serotype typhimurium, and again, looking at a different substrate. They looked at fresh pork loins. The temperature at which the process was applied was 25 degrees. The pressure was slightly higher at 414 megapascals. The d-value in this instance was 1.48 minutes. The same study, though, using Listeria monocytogenes, the d-value at 414 megapascals was 2.14 minutes, which would certainly indicate to us that particularly in this particular food system, Listeria monocytogenes was more resistant to high hypobaric pressure processing at 450 megapascals than was Salmonella serotype typhimurium. Cerevisiae in orange juice, again, Zook and his cohorts in 1999 determined d-values looking at 400 megapascals, 300 megapascals was 10.81 minutes, but as you increased the pressure from 300 to 400 megapascals, the time frame for the d-value was reduced to less than a minute, 0.97 minutes, and further, if you increased the pressure to 500 megapascals, it was 0.18 minutes. And similar results were also seen looking at apple juice as well. So we're looking again at fungi that could possibly be present in an orange juice or an apple juice that could result in spoilage. The effect of high hyperbaric pressure on specific foodborne organisms, and again, here's an instance where we're actually looking at something that could refer to as hurdle technology, where using a combination of potassium sorbate and water activity, and again looking at Z. balii, and they have shown that at the same high hyperbaric pressure and water activity, the time to reduce the detection limit to less than 10 colony forming units, CFUs per mil, is greatly reduced in the presence of potassium sorbate. So potassium sorbate in conjunction with high hyperbaric pressure seems to result in a greater reduction or a faster reduction in the Z. balii in that particular medium. Research on the relative sensitivity of 6 foodborne pathogens. This was performed by Patterson and his cohorts, and they looked at pH 7 buffer, and they determined the high hyperbaric pressure required for a greater than 10 to the 5th reduction in numbers in 15 minutes, and the results we'll see actually on the next slide. So if we looked at the particular pathogen, so we're looking at the time to greater than a 5 log reduction in no more than 15 minutes at a pressure of 275 megapascal Yersinia intercalatica. We got greater than a 10 to the 5th reduction. At 350, Salmonella serotype typhimurium. At 375 megapascals were required to get a greater than a 5 log reduction with Listeria monocytogenes. If we look at Salmonella serotype enteritidis, it required 450 megapascals of pressure to get greater than a 5 log reduction. For Staph aureus, greater than it took 700 megapascals to get greater than a 5 log reduction. And then for E. coli 157H7, again, 700 megapascals were required. So as you look at this, and you think of food applications for high hyperbaric pressure processing, one needs to have some concern or some knowledge perhaps of the particular food product they're processing and what might be the most likely potential foodborne pathogen that would be present. particularly as one looks at using this technology in the case of getting this method approved for fruit juices, again, where one is looking at the requirement for having a HACCP plan in place, where you would need a greater than a 5-log reduction, and one would need to be able to demonstrate that. So you have to be aware of what potential foodborne pathogens might be most likely associated with the food product that you're looking at using this technology to process. Again, the destruction of 2 strains of Listeria monocytogenes at 375 megapascals. And again, looking at treatment time and looking at the log reductions in strain 1 versus strain 2, it becomes very, very evident looking at this data that there are certainly strain differences in the same organism in terms of getting a reduction. Certainly strain 1 is much more resistant to high hypobaric pressure than is strain 2. It's much more easily destroyed than is strain 1 at the same 375 megapascals. Microbiota of vegetables are essentially unaffected at 100 and 200 megapascals at 20 degrees C for 10 minutes or 10 degrees C for 20 minutes. At 300 megapascals at 10 degrees C for 20 minutes was found to be effective. 350 megapascals was needed to reduce most gram-negative bacteria and molds, but if we are looking again at gram-positive bacteria, they weren't totally reduced even at 400 megapascals. So again, going back to that slide where we showed the relative sensitivity of different types of cells to high hyperbaric pressure, this again is something that needs to be taken into consideration as we look at this particular processing technology. High hyperbaric pressures greater than 300 megapascals have been associated with some undesirable changes in vegetables. I mentioned this early on in the presentation, and this will just give you some indication, certainly. At greater than 300 megapascals, the skin on tomatoes loosen and peel away, which in some instances we might not want to happen, but if you're looking at removing tomato skins, this may be an application or a processing technology that could be used for that. Lettuce that had been processed at pressures greater than 300 megapascals remained firm, so we didn't get it actually being destroyed, but it browned. And my question to you is, what does this suggest in terms of enzyme sensitivity? Spinach leaves processed lost nutrients, 400 megapascals for 30 minutes at 5 degrees. And most likely this may be, a lot of this nutrient loss may be a result actually of the nutrients being able to be removed from the cell. Encapsulated viruses, cytomegalovirus and herpes simplex 1 have been reported to be inactivated at 300 megapascals at 25 degrees for 10 minutes. The mechanism appears to be damage to the viral capsule, which actually prevents that virus from actually binding to the host cell. And if it can't do that, then it can't actually use the host cell for replication of the virus. CO2 under high pressure is considerably more antimicrobial than under atmospheric conditions, and my question to you is why? What happens when you put CO2 under high pressure that makes it more antimicrobial than it would be at, say, atmospheric conditions? It's been examined in distilled water, broth, and several foods: chicken, meat, egg yolk, and shrimp. If one looks at the effect of high hyperbaric pressure on fish enzymes, and again, this would be important in looking at the shelf life of fish using this, and one can see that looking at cathepsins, trypsin, and chymotrypsin, that the percent activity lost using high hyperbaric pressure varies, certainly with the enzyme, and it varies also with the fish species. As one looks at these two types of fish species, one of the major differences as one looks at these is comparing sheephead to bluefish. If one looks at the lipid content, bluefish tends to have a much higher lipid content certainly than does sheephead. And this seems to allow actually the enzymes in bluefish to be more sensitive to hyperbaric pressure than it does in sheephead. The most logical application for hyperbaric pressure appears to be a shelf life extension of high acid and semi-preserved foods. As we mentioned previously, it can be part of hurdle technology in combination, say, with mild heat or ionophores such as niacin, particularly the vegetative cells of pathogens. Much more research is required before processing can be equated to thermally processed foods in terms of safety and shelf life. High hyperbaric pressure limitations include bacterial spores are not inactivated by pressure alone. Most suitable for acid and acidified foods. Products need refrigeration for shelf life, and non-acid foods for food safety without other preservation methods. Batch process or semi-batch processes tend to be the most likely applications. Total process cost per kilogram is certainly higher than other food preservation methods that you've talked about during this semester, particularly thermal processing. But one thing to remember is the cost has been significantly reduced over the past few years and probably will continue to be reduced as we get a better handle on this particular technology. One of the novel applications, certainly in a publication, is have been looked at and was published in 2012, is reducing allergenicity, and this was a a publication by Lee et al. And they looked at the effects of high hydrostatic pressure treatment on allergenicity and structural properties of soy protein isolate from infant formula. And again, a novel application that certainly might be of value as it relates to allergic reactions. And finally, I have a list of recent publications that you can go to and look. Some of these actually is 2014 being the latest, and that looked at high pressure thermal sterilization, food safety and food quality of baby food purees, and again in the Journal of Food Science. So ones that give you further information related to more recent publications using high hyperbaric pressure processing. And this includes the lecture on high hyperbaric pressure processing.